Okay, let's start with discussion of your semester 2 assignment 1. We go through to question 1. Question 1 asks you, in which reaction does ammonia behave as a boron lauric acid? So you need to know the definition of boron lauric acid. Okay, it is proton donor. Boron lauric acid is a proton donor. So what does it mean by proton donor? Okay, let's use HCl as example because it's the most common acid that you know, and it's a strong acid. So HCl, if reacts with ammonia, okay, HCl donates a proton, so it became chloride, okay, lost proton, right? And ammonia as a base will accept the proton, so become ammonium. So in this case, as a proton donor, HCl is a boron lauric acid. So we're trying to find now in A, B, C, or D, ammonia behaves like HCl in this case. So let's look at ammonia on the left and right of the equation in A. It is ammonia. Okay, this is a product of ammonia. So ammonia forms ammonium ion. In case A, ammonia is a proton acceptor, not a proton donor. So ammonia is not a boron lauric acid in A. So let's quickly check B. B is ammonia on the left, ammonia on the right, no change, NH3 to NH3. So not a proton donor, not a proton acceptor. B is also not the answer. C, okay, ammonia here. Then we have products of ammonia because two ammonia molecules were used. So one ammonia became NH2 negative, the other one became ammonium. So ammonia is a proton donor and proton acceptor in this equation, in this reaction. Okay, so yes, ammonia is a boron lauric acid, though it is also a boron lauric base in C, but just want you to find, okay, which one does ammonia behave as a boron lauric acid. So C is the answer, but let's look at D also. Now D, you don't even start with NH3, so D is not the answer. Answer to question 1 is C. Now let's look at question 2. Question 2, there is an equilibrium given. Nitrogen dioxide, okay, will form a dinitrogen tetroxide. Okay. These two, they have different colors. One brown, the other one colorless. So if equilibrium position changes because of the change in condition, let's say equilibrium position shift to the left hand side. Okay, more NO2 will be produced. More NO2 will be produced, so the color of the whole mixture will become darker brown. Okay, more brown. Now, if equilibrium position shift to the right hand side, forming more nitrogen tetroxide colorless molecules, okay, the whole mixture, the color will become lighter. Okay, from more brown to become less brown. So the color will fade, become lighter. Okay, now let's look at the condition in the answers. Increasing the pressure, increasing the temperature. Now, increasing the pressure will always shift the equilibrium position, okay, to favor the side with less molecules, less number of moles of gaseous molecules. So let's look at left hand side, we have 2 moles of gases. Right hand side, we only have 1. So right hand side, less number of moles of gases. So increasing the pressure will shift the equilibrium position to the right hand side. So the color will become lighter because N2O4 is colorless. Now let's look at the other condition, increasing the temperature. Increasing the temperature, we need to look at the delta H, okay, of this reaction. it is given here, negative means exothermic. Forward reaction is exothermic. So increasing the temperature will always favor, okay, the endothermic direction. Why favor the endothermic direction? Because according to Lee-Chatelier's principle, okay, equilibrium will always shift to counteract, okay, the change that is made to the equilibrium. So increasing temperature favor the endothermic direction to absorb, okay, more heat, so the temperature is lower again. Okay, so forward is exothermic, backward, okay, the reverse reaction is endothermic. So that means this one will favor the backward reaction. Equilibrium shifts to the left hand side, okay, color will become darker. So again, C is the answer for question 2. Question 3, another equilibrium question. You're supposed to calculate Kp, find Kp expression for this equilibrium. Now this discussion will be a bit longer because I'm going to show you two different methods. Okay, method number 1 is a proper method. Okay, is how you find Kp whenever you are given a question. Later, method number 2, I will teach you a shorter one. Okay, for paper 1. For paper 2, you must always use the method 1 that I'm going to teach you later. Okay, now let's look at method 1. So method 1, we are going to find, okay, we need ICE table. And then we need to find mole fraction. Okay, after that, we need to find partial pressure. Okay, then we write Kp expression. And only we substitute in all the partial pressure, we find, okay, the value for Kp. Okay, now let's look at ICE table. So I'm going to build the ICE table here, left hand side. 2Hi forming H2 and I2. Okay, ICE. I'm going to use number of mole because we are given number of moles in the question. First, we start with B number of mole of Hi. Okay, at the very beginning, there wasn't any product, so 0, 0, 0 H2, 0 I2. Initial, yeah, I for initial, C for change in number of moles. Okay. Let's look at what is given in the question. At equilibrium, X mole of hydrogen iodide had dissociated, so change in hydrogen iodide will be minus X mole. Now, can you see in this equation, the mole ratio of hydrogen iodide to hydrogen to iodine will be 2 to 1 to 1. So, if the change in Hi is X, okay, the change in H2 will be X over 2. Iodine also X over 2 because the mole fraction, the mole ratio is 2 to 1 to 1. Now, Hi is a reactant, so it will reduce, the number of moles will reduce, that's why minus X. But products, okay, number of moles will increase because products are being produced. So this become positive, positive. So at equilibrium, we will have B minus X mole of Hi, X over 2 mole of hydrogen, X over 2 mole of iodine. So we have the number of moles of each of them at equilibrium. Now it's time to move on to mole fraction, finding mole fraction for each of them. Okay. Let me change a color of the ink. Okay. I'll use green for mole fraction. So let's find mole fraction. Now, how to find mole fraction? Mole fraction is found by, let's say I'll find mole fraction of Hi. Okay, it is the number of mole of Hi divided by the total number of mole. Okay, so number of mole of Hi at equilibrium is B minus X. Total number of mole will be this whole thing, B minus X plus X over 2 plus X over 2, which is B. So our total number of mole is B. So this will be the mole fraction of hydrogen iodide at equilibrium. Now, mole fraction of hydrogen is the same as mole fraction of iodine because X over 2, X over 2. Okay, so it'll be number of moles of H2 or I2 divided by the total number of mole, which is B. So the mole fraction will be X over 2B. So we have found the mole fraction. Now let's find their partial pressures. Change color again. Okay, partial pressures for each of them. Now, how to find partial pressure? Okay, partial pressure of Hi will be the mole fraction, okay, multiplied by total pressure. Where's the total pressure is given here? P. Okay, so P minus X divided by B will be the partial pressure for hydrogen iodide. So partial pressure for hydrogen is the same as partial pressure of iodine because they have same number of mole in the mixture at equilibrium. So their partial pressures will be X over 2B multiplied by total pressure P. So it is Px over 2B. Right, so we have found mole fraction, partial pressure. Now it's time to write Kp expression. So Kp expression for this equilibrium will be partial pressure of hydrogen, okay, multiplied by partial pressure of iodine divided by partial pressure of the reactant, which is hydrogen iodide here, square. Okay. Now we have the Kp expression and we have all the partial pressures. Now I can substitute in all these partial pressures into the Kp expression to find a value, okay, for Kp. So I need partial pressure of hydrogen, which is Px over 2B, multiplied by partial pressure of iodine, same thing, Px over 2B, okay, divided by partial pressure of hydrogen iodide square. Okay, so P B minus X over B, okay, this whole thing square. All right, now, so I'll get P square X square divided by 4B square, okay, for this denominator, yeah. Now, at the numerator part, okay, P square B minus X square, okay, then here will be B square. So now let me cancel whatever that I can cancel from these two terms. So B square cancel. Okay, P square cancel. Done, right? There's nothing else that I can cancel. Now, the final expression for Kp will be X square divided by B 4 multiplied by B minus X square. So let's look at the answers, which one matches our final answer here? Okay, D. Okay. So for question 3, the answer is D. Now let's look at method 3. This is a very long method, right? But if you are asked to find an expression for Kp in paper 2, you have to use this method because marks will be given to every single part of the working, the mole fraction, the partial pressure, at the end substitution to find the final expression of Kp. Now let's look at question 3. Okay, method 2. This time let's start with method 2. Change it back to red color. So method 2, right? I promise you method 2 will be shorter. Okay. It's a shorter method that I always use for paper 1. First thing is to check number of moles on left and right. Okay, this side, okay, on the left hand side, 2 moles of gases. Right hand side, okay, 1 plus 1, also 2 moles of gases. Now, if number of moles of gases are the same, okay, we use number of mole for all the calculation. Okay, we do not need to find mole fraction. Okay, no need to find mole fraction, no need to find partial pressure. We will use number of moles for everything. Okay, so let's see. IC table is a must. Okay, so 2Hi forming H2 and I2. So ICE. Still start with B, number of moles of Hi, 0 mole of H2, 0 mole of I2. Change is still minus X. This is still plus X over 2, plus X over 2. At equilibrium, for number of moles of Hi is still B minus X. Okay, for H2 is still X over 2. Iodine also X over 2. Now I promise you no mole fraction, no partial pressure. We are going to use number of mole for Kp. So write Kp expression. Okay, it is partial pressure of hydrogen multiplied by partial pressure of iodine divided by partial pressure of Hi squared. This one you cannot escape. You have to write Kp expression. Okay. Now let's do the substitution using number of moles. Okay. So partial pressure of H2 X over 2, partial pressure of iodine X over 2, divided by partial pressure of Hi B minus X squared. Okay. So let's simplify this, expand and then simplify. X over 2 divided by 4, okay, divided by B minus X squared. So the final answer, X squared divided by 4, B minus X squared, Kp. So we still get D as answer, right? So method 2 is much shorter. What do you need to do is to check the number of moles on the left and right. If they are the same, use method 2. Now, unfortunately, if they are not the same, you have to go back to method 1. Okay, now let's go to question 4 now. Which statement about the effect of a catalyst on a reversible reaction is correct? Now, a catalyst will only provide an alternative pathway with lower activation energy for a reaction. That is why rate of reaction is increased when a catalyst is used. Okay, so you have an energy profile diagram. Okay, this is energy. This is the progress of a reaction. So usually we'll draw like this, okay, and we say that, oh, this is the activation energy. Okay, if you use a catalyst, okay, then it will follow another pathway, lower activation energy with catalyst. Okay, this part, okay, EA with catalyst. So catalyst will only increase the rate of reaction. Even if a reversible reaction, okay, also the same thing. Let's say A forming B and C, reversible. So adding catalyst will increase the rate of forward reaction, will also increase the rate of reverse reaction. Why, Casey? Okay, forward reaction without catalyst, activation energy is high. With catalyst, activation energy is low. Now, reverse reaction from product to reactant, right? Without catalyst, activation energy is high. With catalyst, activation energy is also lowered. So rate of forward and reverse reaction will be increased with the use of a catalyst. Okay? But other than that, okay, nothing will change. So let's look at A, B, C, and D. The activation energy of forward reaction stays the same, okay, which is correct, yeah. Uh, using catalyst, sorry, using catalyst, sorry, using catalyst, activation energy of forward and reverse reaction will be lowered. So A is not correct. Okay, this one wrong, should be lowered. Now B, the composition of equilibrium mixture stays the same. Okay, yes, I say other than the activation energy, other than the rate of reaction, okay, nothing will change with the use of a catalyst. So composition of mixture will stay the same. This is correct. So our answer should be B. But let's look at C and D also. The rate of the backward reaction stays the same. No, rate of backward reaction also will be increased, right? So this is wrong. Okay, will be increased. Then D, value of the equilibrium constant changes. Now, equilibrium constant you have learned already in chapter 8, right? It can only be changed with the change of temperature. So adding a catalyst will not change your equilibrium constant. That is why C and D are not our answers. Also, the answer to question 4 is B. Now, for question 5, which of the following statements is not a correct trend in the properties of elements? Okay, correct trend. Okay, going across period 3, effective nuclear charge increases. That is correct. Okay, period 3, uh, across a period, okay, across any period, the proton number will increase. Okay, so when proton number is increased, effective nuclear charge will also increase. So A is correct. Now, B, ongoing across period 3, atomic radius increases. Okay, across a period, proton number increases, effective nuclear charge increases. So electrons, the outermost electrons or the valence electrons will only get closer to the nucleus because number of protons are increasing, right, inside the nucleus. More positive charges particles in the nucleus, then of course electrons are attracted more to the nucleus, so the size will decrease. So this is wrong. Okay, so they say not a correct trend, right? So B is the answer. Let's also check C and D. On going down group 2, reactivity with water increases. Yes, going down group 2, magnesium, calcium, strontium, barium, sizes of the cation sizes of the atoms are bigger. Okay, that means valence electrons are further away from nucleus. Group 2 are metals. Okay, so they lose electrons in reaction to form cations. So if electrons are getting further and further away from the nucleus, valence electrons, I'm talking about valence electrons. So going down the group easier to lose the electrons in reaction, that means reactivity will increase. So this is correct. Now, going down group 17, oxidizing power decreases. going down, okay, oxidizing power decreases. So let's look at chlorine. Okay, chlorine is able to oxidize all the halide ions below it in group 17. Okay, so when bromide is oxidized, it will form bromine, then chlorine will form chloride. Now this is called oxidizing power of chlorine. Now if I have iodine here and I add iodine to a chloride solution, chloride ions will not be oxidized. Okay, this will not happen because iodine has lower oxidizing power compared to chlorine. So only chlorine, okay, or fluorine can oxidize the other halide ions. Those halide ions below them cannot oxidize their chloride and fluoride ions. So on going down group 17, oxidizing power decreases is correct. So the only incorrect trend will be in B. Now let's look at question 6. Question 6 says that if you mix two oxides together in pH 3, okay, solution is approximately neutral. So how to get a neutral solution from mixing two different oxide? Okay, one of them must be basic and the other one must be acidic. So neutralization can occur, solution can become almost neutral. All right. So let's look at A. Sodium oxide is basic. Okay, I have sodium oxide in B also. That's right. Now basic. Phosphorus oxide is a non-metal oxide, so it is acidic. Magnesium oxide should be basic, but the solubility is low. So I still write basic, okay, although it's not so basic. Aluminium oxide is amphoteric, but it is not soluble in water. Okay, this one is less soluble. I have magnesium oxide again, basic, less soluble. Sulfur trioxide, phosphorus trioxide are both non-metal oxide. They are both acidic. Okay, so let's look at A, B, C, and D combinations. A is the only one basic and acidic added together, so they neutralize each other and solution becomes almost neutral. B, basic and basic. Okay, the solution cannot be neutral. It should be more to basic. Okay, alkali solution. C, amphoteric. Okay, aluminum oxide itself is insoluble in water, doesn't contribute to the pH of the solution. And magnesium oxide is sparingly soluble, forms slightly basic solution. So again, solution is not neutral. D, both also acidic oxides. So both dissolve in water, the mixture will become more acidic. So A is our answer here. Now let's look at question 7. Question 7 is about period 3. Okay. There are a few properties of period 3 elements that you need to know. They ask about first ionization energy and also the melting point. Okay. These are the trends that you need to know the graph, the trend. Let's just look at the notes here. First ionization energy and also melting point. I have the graphs here. For first ionization energy, 11, 12, 13. Okay, 11, 12, 13 is like this. Then 14, 15, and 16. So it's generally increasing. Okay, with some exception here. Exception will be between 12, 13, 15, and 16. Okay, so that will be first ionization energy. Now let's look at melting point. Okay, melting point increasing from sodium until silicon. Okay, then go all the way down, phosphorus lower, and increase a little bit again to sulfur, then decrease again to chlorine and also argon. Okay, now let's go back to the question. it says that, oh, there are three consecutive elements. Consecutive means in a row, yeah? No gap between them. So X, Y, Z are in period 3 of the period table. Y has the highest first ionization energy and the lowest melting point. So just now we look at the first ionization energy trend. Okay, 11, 12, 13. Okay, looks like this, right? And 14, 15, 16 looks like this again. So 11 is sodium, 12 is magnesium, okay, 13 is aluminium, 14 will be silicon, 15 is phosphorus, 16 sulfur. So now I have two combinations which can be X, Y, and Z. X, Y, Z, X, Y, Z, right? Okay. But then now we also have to look at the melting point. 11, okay, for melting point, 11, 12, 13, 14, 15, 16. Now 11, 12, 13 increasing. Sodium increases to magnesium, then increase a little bit to aluminium. For 14, silicon has the highest one in period 3, go all the way down to phosphorus. Okay, then increase a little bit for sulfur. It says that Y has the lowest melting point in the combination. See, okay, for first ionization energy, these two are the possible answers. Now, looking at the melting point, okay, phosphorus is the one with the lowest melting point. So our X, Y, and Z will be this combo, this one. So let's look at the answer. It should be phosphorus, silicon, phosphorus, and sulfur. Oh, sorry. I missed out the answer D. Answer should be D, silicon, phosphorus, and sulfur. Sorry, I missed out this answer. So the answer to question 7 is D. Right, let's move on to question 8. P, Q, and R are hydroxide compounds of the element X, Y, and Z respectively. X, Y, and Z are in the same period of the period table. P gives an aqueous solution which is strongly alkaline. Now, whenever I say strongly alkaline, okay, I think of sodium, okay, sodium hydroxide. He reacts with both strong acids and alkaline. Hold on. I actually think this question is faulty. Okay. I think I should change this to oxide. Not hydroxide, oxide. Okay. It makes more sense with oxide. So P is an oxide that gives aqueous solution which is strongly alkaline. P is sodium oxide. They dissolve in aqueous solution, form sodium hydroxide, which is strongly alkaline. Okay. Now, oxide of Q is both can react with both strong acid and alkaline. It is an M4 telluric oxide. Okay, so we know Q is aluminium oxide. R gives an aqueous solution of pH less than 7. Okay, acidic. Acidic oxide can only be sulfur dioxide, sulfur trioxide, okay, or phosphorus oxide. Okay, so sulfur or phosphorus. So X is sodium, Y is aluminium, okay, Z is sulfur or phosphorus. We don't know which one, yeah? But never mind, let's look at which statement is true regarding X, Y, and Z, yeah? Okay, the first ionization energy decreases from X to Y to Z, okay? Can you see that from sodium to aluminium to sulfur or phosphorus is across period 3. First ionization, energy increases. It should be increasing, okay, across a period. So this word is wrong, should be increasing. B, electronegativity increases from X to Y to Z. Yeah, across a period, whichever period in period table, electronegativity will always increase. Now, how do I remember this trend is I always remember group 17 has the highest electronegativity in compared to all the other elements in the period. Group 7 is on the right hand side of the period table. So electronegativity increases for all periods. Okay, so B is correct. Our answer should be B. Now let's look at why C and D are not correct. C, the atomic radius increases in the order of X, Y, and Z. We have seen this already. Atomic radius should decrease, okay, across a period because effective nuclear charge increases across a period. So electrons are closer, more attracted, okay, stronger attraction between electrons and nucleus, so size will decrease. Now D, X, Y, and Z could be phosphorus, aluminium, and sodium. Okay, we just say that X is sodium, Y is aluminium, okay, Z can be sulfur or phosphorus. This order is exactly the opposite from what we've discussed. So D cannot be our answer. Number 8, the answer is B. Number 9, which of the following shows a decreasing trend from magnesium to barium? This is group 2. Okay, magnesium to calcium to strontium to barium in group 2. So which one is decreasing? Reactivity of elements with water, we have discussed this again in, I think, question 5. Okay, if you need the explanation again, please go and look at our discussion on question 5. Okay, but reactivity of elements with water should increase going down the group. Okay, getting more and more reactive. B, metallic radii of the elements going down the group, more and more electrons, right? Okay, and going down groups, you know, when you increase one period, you are increasing one shell, one principal quantum shell in the atom, so the radii will increase. Solubility of the sulfate, okay, barium sulfate is the least soluble one, okay, so correct, solubility of sulfates will decrease going down group 2. Our answer is C. Now D, basic strength of the oxide. Now magnesium oxide, calcium oxide, strontium oxide, and barium oxide, their solubility will increase going down the group. So if dissolve more, okay, forming more alkaline solution, so basic strength of the oxide should increase. Okay, so this is also increasing. That's why our answer confirm is a C. Now, question 10 is a calculation question. On heating, magnesium will react with element X to form compound Y. Okay, magnesium reacts with X, forming Y. An aqueous solution of Y when treated with aqueous silver nitrate gives a white precipitate. Okay, something reacts with silver nitrate gives white precipitate. That white precipitate is AgCl. So Y is a chloride. Okay, in this case, we know, okay, it is actually magnesium chloride. If Y is magnesium chloride, what is X? X is chlorine. Okay, so let me rewrite the equation. It should be Mg plus Cl2 forming magnesium chloride. Now this reaction, this equation is already balanced. Okay, great, very easy, 1 to 1 mole ratio. And okay, this white precipitate is readily soluble in aqueous ammonia. Okay, confirm AgCl. What's the minimum mass of X that's needed to react with 4.05 gram of magnesium? Okay, now I have the equation already. So we are supposed to find chlorine, the mass of chlorine to react with magnesium. Let's find number of mole of magnesium. 4.05 divided by the atomic mass of magnesium, which is 24.3. So if I use my calculator, it is 0.167 mole. Now, according to the equation, 1 mole of magnesium will react with 1 mole of chlorine. So the number of moles of chlorine is the same as the number of mole of magnesium, which is 0.167 mole. So how to find the mass of chlorine? Will be the number of mole multiplied by the molecular weight of the molar mass of this chlorine, 35.5, multiplied by 2. So it should be 11.83 gram A. Now, question 11, radium is the last element in group 2. Usually we learn until barium. Okay, now they want to add one more into the trend, which is radium. Radium is below barium. Okay, in periodic table, which of the following is not true for radium? A, oxide is basic in water. Okay, this is correct. All group 2 oxides are basic in water. B, it reacts with water to release hydrogen gas. Yes, even magnesium oxide, okay, even magnesium, sorry, not magnesium oxide, even magnesium will react with water to release hydrogen gas. So all group 2 elements will react with water to release hydrogen gas. It is the least reactive element in group 2. You can go back and look at question 5 and 9. Okay, I've discussed about the trend of group 2 already. Going down group 2, okay, the element should become more and more reactive. So this is not correct. Since it's the last one, it should be the most reactive. Not true, not true. So our answer is C. D, its compound may conduct electricity when molten. Okay, correct. Okay, group 2 compounds, when they are molten, they have free moving cations and also anions, so may conduct electricity. So our answer to question 11 is C. Now let's look at question 12. When a mixture of white solids X is treated with an excess dilute hydrochloric acid, colorless gas is evolved, okay, and some but not all of the mixture dissolves. White solid treated with acid, okay, and gas is formed. Okay, X is a carbonate. Okay, only carbonate will react with acid to form carbon dioxide gas. Okay, so X is carbonate. Um, sorry, X is mixture of solid, right? So X contains carbonate. Okay, a mixture. So one of the solid must be a carbonate. That's why it can react with acid to form carbon dioxide gas. And the next part of the question says, yeah, some but not all of the mixture dissolves. So that means we must still have some solid remains undissolved in the mixture, okay, after treated with acid. So let's look at A. Calcium carbonate will react with acid, okay, and dissolve in acid. So CaCO3, okay, if I add HCl, okay, it will form CaCl2, H2O, and also CO2. Yeah. CaCl2 is soluble in water, so you won't see CaCl2 as undissolved solid. Magnesium sulfate is also soluble in water, so combination of calcium carbonate and magnesium sulfate in A, okay, you won't see any undissolved solid at the end. So A cannot be mixture X because mixture X say that there must be some solid they are not dissolved, right? B, calcium hydroxide. Okay, calcium hydroxide is a base. It will react with HCl, okay, to form calcium chloride, and then to also form H2O. Okay, so 2H2O. Again, calcium chloride here is soluble in water. Magnesium carbonate reacts with acid to form magnesium chloride, a soluble salt also. So combination B again, okay, products are all soluble, so cannot be the answer because we want some of the solids not dissolved, yeah. Now let's look at C, barium sulfate. Now barium sulfate is not base, it will not react with acid, okay, and barium sulfate is an insoluble salt. So you will see barium sulfate uh, remains as solid in the solution from beginning until the end. Okay, this is what we want, right? We want some solid not dissolved in the solution. So now C could be our answer. Let's look at calcium carbonate, another solid inside X. Calcium carbonate, okay, will react like this. Form calcium chloride, which is soluble. But, okay, at the end, we will still see this barium sulfate solid in the solution. So C is our answer because the question is some but not all of the mixture dissolved. Now let's look at D. Barium nitrate. Okay, barium nitrate is soluble in the solution. Okay, although it doesn't react with HCl because it is not a base, but it is soluble. So you won't see barium nitrate solid in the solution. Calcium hydroxide will react this way with HCl, forming a soluble salt. Okay, so combination D will not give any undissolved solid at the end. So C is the answer. Question 13. Okay, boiling points of the halogens increase down group 17. Okay, because of intermolecular forces. Boiling point always relate, okay, always relate boiling point to intermolecular forces. Group 17 halogens are all diatomic atoms, Cl2, Br2, I2. So going down the group, okay, um, they all have more and more number of electrons. Okay, and increasing in number of electrons will contribute to stronger ID forces. And these diatomic molecules, they are non-polar. So they only have ID forces between them. So increasing in the number of electrons going down the group will make these ID forces between the molecules to be stronger. Okay, so let's look at the answer now. Why boiling points of halogens increase down group 17? Number of electrons increases. Okay, so A is our answer. Not because of electronegativity, because it's non-polar. Okay, increase in electronegativity will not contribute to stronger intermolecular forces. Covalent bond strength increase. Okay, we're not talking about covalent bond. We're not talking about intramolecular forces. We are talking about intermolecular forces. The distance between the atoms increase. Okay, this is also about the bond, so not our answers. Okay, A is our answer. Question 14. Okay, question 14, a reaction scheme is given and they say X is one of the halogens, chlorine, bromine, or iodine, or astatine. Yeah, oh, astatine is also given. Okay, X will react with silver nitrate, form precipitate. Okay, all of them will react with silver nitrate to form precipitate. This will not give us the answer. Let's look at once ammonia is added to the precipitate. Okay. Ammonia is added to precipitate, then it forms a colorless solution. So that means this precipitate is soluble in ammonia. So this precipitate is AgCl. Because AgBr, AgI, now Ag acetate, okay, also will not dissolve in ammonia. Only AgCl will form a colorless solution with ammonia. So X is a chloride. And, okay, which one has chloride? A, B, C, D? Only A. So A is our answer. The other parts of the reaction scheme is not important in finding your answer, so you can ignore them. Question 15. What happens when chlorine is bubbled through aqueous potassium iodide? Okay, I think we have mentioned this before already in the oxidizing power of group 17. Again, in question 5, yeah, we talk about the oxidizing power. Chlorine can oxidize bromide ion, can oxidize iodide ion, all the halide ions below chlorine, okay, in the group 17. Okay, so when they are iodized, they are oxidized, they form the elements, and chloride ions are also formed. Oh, sorry, no two here. Okay, so let's look at the answer. We have iodide, yeah, so we focus on this equation. Chlorine is oxidized, no. Chlorine is reduced, right? Chlorine is oxidized again, no. Iodide ions are oxidized to iodine, okay, correct. There is no observable reaction, or definitely not correct, okay. Chlorine is a yellowish gas, okay, so you should see some observation because it becomes chloride ion, so the yellow gas disappears. Question 16. On reacting solid bromide ions with concentrated sulfuric acid, which of the following compounds will not be detected? Okay, a concentrated sulfuric acid with NaCl, okay, we get HCl. So this is a white film. Okay, with NaBr, you get HBr, a white film. But further oxidation of HBr will occur. Okay, you get bromine, which is a brown film. Okay, because this reactor is actually very exothermic. So I know bromine should be a liquid at room temperature, room condition, but because heat is also produced, so bromine easily vaporized to become brown film. And then you also will see SO2, I think. Okay, SO2. Now, SO2 is a pungent gas, okay, which can be easily oxidized to SO3 by using KMnO4. Okay, that's why decolorizes KMnO4. Okay, right. With NaI, more complicated, HI, white film. I2, okay, the purple vapor or black solid. You see SO2 also, pungent gas. Now I'm just showing you all of them, okay. I know for iodide one is not required, chloride also not required. I just want to show you, okay, everything. You have H2S, you have sulfur, yellow solid. Okay, this is a rotten egg smell. Yes. Okay, why did I list down all this is because I just want to teach you one of the methods that I use to remember all this. With sodium chloride, okay, only one product is formed. With NaBr3, okay, with iodide 5. So remember this 1, 3, 5. Okay, one product, three products, five products, an odd number. So when you remember this 1, 3, 5, then for these three halide ions with concentrated sulfuric acid, you'll be able to list down, okay, what are the products that are formed, okay, when they react with concentrated sulfuric acid. Now, of course, I know this question we have to focus on bromide. Okay, so this one. So which one is not detected? Okay, hydrogen bromide, white film, brown film, pungent gas. So H2S is not produced. H2S will only be produced when iodide reacts with concentrated sulfuric acid. So for question 16, our answer is B. Now for question 17, nitrogen is frequently used as an inert atmosphere because it is an unreactive gas. Okay, nitrogen is very unreactive because it has triple bond between the two nitrogen atoms in the molecule. So C is the answer. Now why A, B, and D are not our best answer? Yeah, let's look at A. Bond energy of molecule is high. Now bond energy is high because the bond is a triple bond. So because of this, contribute to this. Now B, the bond in its molecule is very short. Okay, because it's a triple bond, that's why it's very short. Okay. D, the three p orbitals of nitrogen are half filled, not really because of that. That's why it's inert. So D definitely not our answer. And A and B is because of C. So C is the best explanation for the unreactivity of nitrogen. Now, nitrogen and carbon monoxide both have molecular weight of 28. Boiling point is for nitrogen is 77. For carbon monoxide is 82. Now, again, boiling points, okay, we have to relate it to intermolecular forces. Okay, N2, both ends of the molecule is nitrogen, right? Both also nitrogen, so this is a non-polar molecule. And then CO, okay, C and O polar molecule because oxygen is more electronegative than carbon atom. Okay, so polar molecule, between non-polar molecules, you only have weak ID-ID forces. Between polar molecules, you have stronger PD-PD forces. So what could be responsible for this difference in boiling point? PD-PD forces are stronger than ID-ID forces. So that's why higher boiling points for carbon monoxide. Let's look at A. Nitrogen has strong triple bond. Carbon monoxide has double bond. Okay, no, we are not talking about the covalent bonding. We are talking about intermolecular forces here. B. The carbon monoxide molecule has more electrons than nitrogen. No. Okay, not because of that. Because we're not talking about ID forces only. We are talking about PD forces in carbon monoxide. C, nitrogen has pi and sigma bond. Carbon monoxide has sigma bond only. No, since it has double bond, right? It should have pi bond also, but doesn't matter. Sigma bond, pi bond, they are covalent bonding. Okay, inside the molecule, not between molecules. The CO molecules have a permanent dipole. Nitrogen molecules are not polar. Okay, that is our answer, right? From our discussion, we want to know their intermolecular forces, so we just only talked about their polarity. Okay, second last question. Question 19. Which statement about ammonia is completely correct? Okay, let's look at it. Ammonia is a base, correct? Accepts hydroxide ion. Okay, no. Okay, a base should accept hydrogen ions, so A is not completely correct. B, ammonia acts as a nucleophile by accepting a pair of electrons when it reacts with bromoethane. Now, ammonia is a nucleophile. So it likes nucleus is because it can donate lone pair. Okay, you'll be able to donate a pair of electrons, not accept a pair of electrons. C, ammonia can form a coordinate bond with hydrogen ion to form an ammonium ion. Alright, that's correct. Okay, ammonia has a lone pair on the nitrogen. So when it reacts with hydrogen ion, okay, hydrogen has one s orbital with no electrons, right? So because it loses only one electron, that's why it became hydrogen ion, H plus. So it has empty orbital to accept the lone pair. So ammonium ion can form, okay, a coordinate bond or additive bond is formed between nitrogen and hydrogen here. Okay, ammonium ion is formed. So C is completely correct. D, the shape of ammonium molecule is pyramidal. Pyramidal is correct. Bond angle 109.5. Okay, bond angle is not correct. This bond angle should be 107 degrees. So the only completely correct one is C in question 19. Right, last question of this assignment. Compound T is a white crystalline solid. When a sample of T was mixed with aqueous sodium hydroxide and heated, okay, this reaction, pungent smelling gas was produced. Something reacted with sodium hydroxide, a base, and then pungent smelling gas is produced. This pungent smelling gas is ammonia. So what kind of compound can react with a base to form ammonia? Okay, it is an ammonium salt. So T, compound T has ammonium ion. Then after that, to confirm, we look at the gas turned damp red litmus paper blue, confirm is ammonia. This same gas produce dense white smoke with hydrogen chloride, which is correct. Okay, HCl will react with ammonia to form ammonium chloride. Ammonium chloride is white smoke. Okay, because it is actually a solid, but because it is formed very slowly, uh, molecule by per molecule, okay, being formed, so they are very light. They disperse this solid too light, so they float in the air. So you see as white smoke. Okay. Now further testing of a solution of P with barium chloride solution. Okay, barium chloride solution contains barium 2 ions, produce a dense white precipitate. Barium ion forms a white precipitate. Okay, it is barium sulfate. So that means in compound T, we have sulfate ions also. So what's the identity of compound T? Okay, identity of compound T is ammonium ion and sulfate ion. So ammonium sulfate. Okay. Oh, sorry, I forgot, right? This white precipitate did not dissolve in acid. So confirm is sulfate, not sulfide. Okay, not this one. It's SO42 minus. Ammonium sulfate is our answer. A, okay, A is ammonium sulfate. So the answer to question 20 is A. Now, please, okay, open your assignment 1, okay, on Teams. I've discussed all the answers already. Okay, please do please answer all the questions on Teams Microsoft Forms and then submit your assignment. Okay, deadline is today, so submit before 11:59.